this discussion, we will learn how to calculate range, standard deviation and standard error, and how these measures of dispersion can be used in statistics. We have already learned that frequency distribution tables gives a rough idea about the distribution of variables in a sample or in a population, while mean, median and mode explain the central tendency of the distribution. But none of these measures describe how the data are spread with respect to the central values. Now, in a normal distribution, all the measures of central tendency, that is the mean, median and mode, will be the same. That is, all the values of mean, median and mode will be occupying the same position, and there is a gradual decline in slope on either side of the mean. Look at this diagram. You see mean, median and mode centrally located, and on either side the slopes declined gradually. But the spread of data is not always gradual or smooth, as you have seen in the diagram. They may be dispersed widely or moderately or shortly. The following diagram will show that there is one distribution, blue line, which is we call platykurtic, that is a flat distribution. That means data are distributed widely. The next one in green color, mesokurtic, which is otherwise we call normal distribution, and with the red line we call it leptokurtic, that is the data are less spread around the central values. Now, dispersion is the spread of the values of a variable on either side of the central value, and there are different measures, as I said earlier: range, standard deviation and standard error. The first is range. Now, it is the difference between the lowest and the highest value of a data set when the data are arranged in array. Larger the range, greater is the dispersion of the values. Let us have a look at the table. You see here the table, the lowest value, I have marked it, is 45 and the highest value is 85. Now, if I am to calculate the range of this data, we will subtract 85 minus 45, or otherwise you will subtract 45 from 85 and you will get 40 as a value for range. Had the highest and the lowest values of the distribution been 45 and 62 respectively, the range would have been smaller. So 62 minus 45 is 17. Earlier it was 40 and now it is 17. But the range does not always give a satisfactory result of dispersion because it is affected by extreme values. For example, if there is one value 10 in the distribution, then the range would have been 85 minus 10, that is 75, since there is no other value between 45 and 10, and the range of the distribution thus gets affected. We can think of another measure of dispersion which is called mean deviation. Now here the deviation, that is measured in terms of absolute values of each value from the mean, is calculated, and the arithmetic mean of these deviations is measured. The formula for calculating the mean deviation from a group data is as follows. Look at this table. You see weight in kg, 44.5 to 50.5. This is the first class interval. Second, 50.5 to 56.5. And the class marks, corresponding class marks and frequencies are provided. And how we calculate? First, you see the formula. F1 within the modal range, the difference between A1 and A next plus F2, A2 minus A, F3, A3 minus A, and so on up to Fn, An minus A, and the whole is divided by capital N, that is the total number of observation. Here, F1, F2 to Fn are the frequencies of first, second, and nth class intervals. A1, A2, to An are the class marks of first, second through nth class intervals. A, that is the capital A, is the arithmetic mean of all observations, and capital N is the total number of observation. Thus, applying that formula, we can derive the arithmetic mean, and it comes to 9.16. See how I have calculated using the formula. First, I'll just give you the clue from the first one. You see, 3 is the frequency of the first class interval, 47.5 is the class mark of the first class interval, and 65.0 is your mean. So in this way, the mean deviation has been calculated, and it comes to 9.16. The formula for this mean deviation can be condensed as summation I Fi within bracket Ai minus capital A bracket close whole divided by n, where Fi is the frequency of the ith class, Ai is the class mark of the ith class interval, capital A is the arithmetic mean, and n is the total number of observations. Measure of dispersion from the mean has an advantage over the preceding measures of dispersion because it considers all the values of the variable in estimating dispersion, and the unit of standard deviation is the same as that of mean. For example, if the unit of the mean of all the values is in centimeter, the standard deviation, in case of standard deviation, the unit will also be in centimeter. This is one very important advantage. Standard deviation is defined as the square root of the mean squared deviation, and the formula can be worked out in the following way. First, number 1, first find out the difference of all the values independently from the mean. Second, square each of this difference. In the third step, add all the squared differences. In the fourth, divide the sum of the squared difference by the total number of observations to get the mean deviation. And finally, you square root the expression to get the standard deviation. In fact, square root of the expression reverses the unit of measurement to its actual state. The formula for standard deviation can thus be written as square root of x minus x bar whole square divided by n. If the sample size is small, the formula is slightly modified. Instead of dividing it by n, we divide it by n minus 1. Now you may inquire, what is n minus 1? N minus 1 is called the degrees of freedom. The degrees of freedom, or which has an acronym, we say DF. The degrees of freedom are the number of values in a set of data which are unrestricted, that is independent and free to vary. Let me give a quick example. Suppose the sum of x, y and z is 12, and if x equals to 4, y equals to 5, then z must be equal to 3, so that x plus y plus z is 12. Thus, when there are 3 numbers, the degrees of freedom will be 3 minus 1, that's 2. Likewise, the DF, or the degrees of freedom, for 5 numbers is 4. We use the concept of degrees of freedom when the sample size is small. Now let us come back to our original discussion. Now, the formula that I mentioned can be applicable for ungrouped data. But to work out with a group data, the formula will be a bit different. Let us look at this table. You see, here I have presented the height of certain individuals, say for example 100 individuals, and the distributions are here. The class mark for each class interval, the frequencies of the corresponding classes, the mean is presented 167.45, and here what I have done, I have find out the deviation of the mean from each of the class marks. And the first one is minus 6.45, the second is minus 3.45, and so on, you can see. In the next column, I have squared this deviation, x minus x bar whole square. And in the last column, I have multiplied the corresponding frequencies with the differences, with the squared differences. And if you look at the last row, you will see here I have done summation f, that is the addition of all the frequencies, that is the total number of observation. Last cell of the last column, you will find I have performed summation f x minus x bar whole square, that is the addition of all the values of x, f multiplied by x minus x bar whole square. And in this way, we get a formula for standard deviation, that is summation f x minus x bar whole square divided by n, and the entire expression is square rooted. Thus, from the above distribution, we get a value of the standard deviation 2.91 centimeter. Now, and from this table, see how I have calculated the same distribution I have used here. What I did, I multiplied first f with x, and you see the fourth column, all the values of fx, and in the fifth column, I squared the class mark and then multiplied by f, and thus we get the values for fx square. And if you look at the last row, you find summation f, that is the total number of observation 100, summation fx, and on the last one you find summation fx square. As the value is derived from square root, plus minus symbol is used before writing the value of standard deviation. The symbols that we use in standard deviation for population and sample are different. In case of sample, it is small s, and in case of population, we use the symbol sigma. Generally, standard deviation is presented along with mean plus minus 1 SD, or simply we write mean plus minus SD. From mean and standard deviation, one can get an idea about the spread of the values of a variable on either side of the mean. Larger the value of the standard deviation, greater is the spread of the values of the variable around the mean. And this indicates that in the data, heterogeneity is present. For example, mean and standard deviation of height of a group of individuals, if I say, is 145.25 plus minus 2.5 centimeter. What does it mean? This means that if the data follow a normal distribution, then 68.26% of the values of the variables, here it is height of all the individuals, will fall within the range 145.25 minus 2.5 centimeter to 145.25 plus 2.5 centimeter. That is, between, if you calculate these two values, we will get the range between 142.75 centimeter and 147.75 centimeter. Again, mean plus minus 2 SD means that the spread of the values of the variable around the mean is between 145.25 plus 2 into 2.5 and 145.25 minus 2 into 2.5, that is between 150.25 centimeter and 140.25 centimeter. And we can say that 95.44% of the values of the variable will come into this range. Similarly, mean plus minus 3 SD will include 99.73% of the values of the variable. Look at this normal distribution figure, and you can see nicely depicted that the central position, which is mu, where it is, that is the position of the mean, and you see minus 1 SD, mu plus 1 SD, again mu plus 2 SD, mu minus 2 SD, 3 SD, and minus 3 SD. However, if the distribution of data is skewed, then the standard deviation will be affected by outliers. In a skewed distribution, the values of mean, median, and mode are not the same, and they do not occupy the central position. Let us have a look at the diagram here below. Look at this. You see, it is unlike a typical normal distribution. Here it is negatively skewed. That is, the distribution is more towards the right side. And see, the position of mean, median, and mode are not the same. Or it can be skewed to the left, that is, most of the data are distributed towards the left side. Here also you find that the mean, median, and mode are not on the same position like the normal distribution. Now, the last part of the dispersion measures is standard error, which has an acronym SE. This is another measure of dispersion of mean. It is the standard deviation of the sampling distribution of the means. And the formula for standard error is provided in the screen. SE is equal to S divided by square root of n, where S is the standard deviation and small n is the sample size. Standard error is useful when one compares the dispersion of two different data set of unequal sample size, and that is drawn from the same or from different population. Suppose the mean sitting height vertex of 64 individuals is 68.2 centimeter and the standard deviation of the mean is 4.0 centimeter. The standard error will be 4.0 divided by square root of 64, and that will give you a value is 0.5. The mean and standard error is represented in this way. You see, 68.2 plus minus 0.5. Thus, we can conclude that this module deals with the dispersion of data in a population or sample. Data are not always found to be distributed uniformly surrounding the central value. The knowledge of dispersion of data is prerequisite to carrying any further data analysis. Dispersion of data also helps a researcher to understand the degree of heterogeneity in the data. So, greater the heterogeneity, more will be the degree of dispersion. There are various measures of dispersion that we discussed: range, standard deviation, standard error, and variance. Each has its own merits and demerits. But standard deviation so far has an advantage over any other measures of dispersion since its unit is the same with that of the mean.